Pluto and the possibility of a cosmic collision. Pluto is a distant and stealthy, more unpretentious planet that was once a part of our nearby planetary system. However, advancing and disturbing announcements by leading astrophysicists Neil deGrasse Tyson and Makaku have brought Pluto back into the spotlight. They proposed that this chilly world is on a potential collision course with Neptune. But how could this really happen? And what might be the consequences of such an enormous event? Are we seeing a bewildering, huge erraticism, or is there something else to this looming setback? Join us as we take a closer look at the potential outcomes of a Pluto-Neptune impact. Pluto, a former planet that was reclassified as a dwarf planet, remains a subject of interest and study in the vast universe. According to recent hypotheses from leading specialists, Pluto's orbit is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Makaku are both raising the alarm about a potentially hazardous collision between these two planetary bodies, an event that could represent a massive risk to Earth. Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a dazzling 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's orbit is marked by its particularly elliptical shape, deviating widely from the nearly circular orbits of the major planets. What makes Pluto's orbit even more surprising is its inclination of about 17 degrees to the ecliptic plane. Its path is significantly more irregular than that of the other planets. This tendency and unpredictability add layers of complexity to its orbital arrangement. Perhaps one of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect from their respective positions in the solar system. Astronomers began examining Pluto's orbit shortly after its discovery. Initially, they tried to determine its unique path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out for its deep inclination and erratic shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit, despite these complexities, is a testament to the nuances of celestial mechanics. One key to this puzzle is the three-body problem in space, which involves determining how three objects, like Pluto, Neptune, and the Sun, move and influence each other through gravity. It's like trying to predict their trajectories based on their initial positions and mutual gravitational pulls. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity interact in complex ways. The terms non-concurrent libration, orbital precession, and VZK wobbling are central to this discussion. Non-concurrent libration. When Pluto crosses Neptune's orbit, it is never in the same position as Neptune. It is always at least 90 degrees away in orbital longitude. This spatial offset is critical in preventing a collision. Orbital precession refers to the gradual shift in the orientation of a planet's orbit. For Pluto, this means that when it comes close to Neptune or any other giant planet, it is typically well above or below their orbital plane, providing another safeguard against impact. VZK wobbling, named after three researchers, Zell, Kai, and others, who studied how three-body gravitational interactions influence the motion of celestial objects. In Pluto's case, VZK wobbling helps explain the unusual nature of its orbit near the Sun. Despite appearances of chaos, this wobbling contributes to the long-term stability of Pluto's path. These dynamics show that even though the motions of celestial bodies may seem wild and unpredictable, hidden patterns and gravitational rules maintain a degree of order. These forces help ensure that Pluto doesn't collide with Neptune or drift off course. This three-body interaction is essential to understanding how orbits change due to gravitational forces. It helps us learn more about Pluto, our solar system, and even exoplanetary systems. Numerical simulations from the late 1980s showed that despite these stabilizing influences, Pluto's orbit is fundamentally chaotic. Even tiny deviations in initial conditions can lead to vastly different outcomes over centuries. Still, Pluto's orbital peculiarities have been found to maintain stability over extremely long timescales. Further analysis revealed how the giant planets, especially Neptune, Jupiter, and Saturn, affect Pluto's orbit. Notably, Pluto and Neptune have a 3:2 orbital resonance, meaning that for every 2 orbits Pluto completes, Neptune completes 3. This resonance helps maintain their separation. But Neptune isn't the only guardian. Jupiter's immense gravity plays a colossal role in stabilizing Pluto's orbit, and Saturn contributes as well. These forces combine to keep Pluto on a relatively steady path, potentially for millions of years. Without these mechanisms, the solar system would be far more chaotic. Planets like Pluto could be ejected from orbit or collide with others, triggering chain reactions of gravitational disruptions. The idea of a Pluto-Neptune collision sparks curiosity and concern. Understanding Pluto's orbit is critical, as it gives us a clearer picture of our dynamic solar system. Even seemingly unstable orbits can reach a state of balance thanks to gravitational interactions and orbital mechanics. This also underscores the importance of constant observation and simulation. The concept of orbital chaos, the sensitive dependence on initial conditions, is vividly demonstrated by Pluto. Even the smallest changes in speed or position can produce radically different outcomes. Automated simulations have been invaluable for modeling Pluto's movements. By slightly adjusting variables, scientists can observe how minor differences dramatically impact its trajectory. These simulations show that even with mechanisms like orbital resonance and vibration, Pluto's orbit can still be inconsistent. Yet, paradoxically, this chaotic orbit remains stable over billions of years. There's a kind of order within the disorder, a harmony within chaos. Still, predicting the long-term evolution of such a system is difficult. Our numerical models are only as good as their inputs, and even small uncertainties can lead to unpredictable results. Neil deGrasse Tyson, renowned for reclassifying Pluto as a dwarf planet, continues to draw attention to its unique orbital dynamics. While his renaming of Pluto was controversial, it reflects the expanding boundaries of astronomical knowledge. Tyson sees the complexities of Pluto's orbit as a symbol of how much more we have yet to learn. Despite his generally optimistic outlook, Tyson has voiced concern about Pluto's future. If its orbit continues to change, even slightly, it could one day intersect Neptune's path in a catastrophic way. Would Neptune survive? Would Pluto be shattered? The answers remain unknown. Currently, there's no solid evidence suggesting a collision is imminent. Tyson's warnings emphasize not the certainty of a crash, but the danger of underestimating orbital complexities. As our understanding of celestial mechanics evolves, it's crucial to continue monitoring these interactions. From dwarf planets to gas giants, every body affects the others in subtle but profound ways.